Look at your hand. Turn it over. See the lines, the texture, the solid, dependable presence of it. It feels real, does it not? It feels like a thing, an object in the world, separate from the air around it, separate from the chair it rests upon, separate from the body it is attached to. This feeling, this deep, instinctual certainty of solidity is the first and most profound lie your senses have ever told you. It is a necessary lie, of course, a survival trait. To navigate a world of predators and precipices, you need to believe in the hardness of the rock and the emptiness of the air. But it is a lie nonetheless, a beautiful, functional, and utterly convincing illusion. Beneath the skin, beyond the cells, past the molecules and the atoms, you arrive at a place where the rules of solidity and separation dissolve. You arrive at a place of pure mystery. You arrive in a world populated by ghosts. Not the ghosts of storybooks, not the lingering spirits of the dead. These are something far more fundamental. They're the ghosts in the machine of reality itself. They're the architects of the substance you feel, yet they possess no substance of their own. They're the notes that compose the symphony of matter, but you can never hear a single note played alone. They have a name, a whimsical, almost nonsensical name for something so foundational. It is a name plucked from a dreamlike book, a name that seems to wink at the absurdity of it all. They're called quarks, and they're not real. Not in the way you understand the word real, not in the way your hand is real. And yet, without them, your hand would not exist. Without them, nothing would exist. How can this be? How can the foundation of all existence be something that cannot, even in principle, be isolated and held up to the light? How can the universe be built from bricks that evaporate the moment you pull them from the wall? This is not a riddle. This is not a metaphor, not entirely. This is the central, maddening, and ultimately beautiful truth of the physical world. To understand it is to let go of the world you think you know. It is to accept that you are woven from paradox. Let's begin that journey. Let us deconstruct the illusion. The first step is a familiar one. You have heard it before. The atom, the supposed building block of the ancients, is mostly empty space. If the nucleus were the size of a marble in the center of a grand cathedral, the electrons would be motes of dust dancing in the far-off rafters. The space between them is vast, an echoing void. The solidity you feel, the pressure of your fingers against a tabletop, is not the meeting of two solid things. It is an argument between forces. It is the electromagnetic repulsion between the electron clouds of your atoms and the atoms of the table. You have never truly touched anything in your life. You have only ever felt the pushback, the fierce refusal of one field of influence to occupy the same space as another. But this is only the first veil to be lifted. It suggests a universe of tiny, hard bits separated by immense emptiness. A solar system model of reality. This is still comfortable. It is still intuitive. We can still imagine the hard little marble of the nucleus. But we must go deeper. We must journey into that marble. The nucleus is where almost all of your mass resides. It is the anchor of your being. It is composed, as you were taught, of protons and neutrons. For a long time, these were considered the end of the line, the fundamental particles, the truly solid bits from which all else was made. This, too, was a comforting illusion, a necessary fiction for a simpler time. Imagine a proton not as a smooth, perfect sphere. Imagine it instead as a cage, a frantic, violent, seething cage of energy. And inside this cage are prisoners, 3 of them forever bound together. These are the quarks. They're not sitting calmly. They're thrashing against their bonds, moving at nearly the speed of light. They're surrounded by a roiling, boiling soup of other entities, virtual particles and force carriers that flash into and out of existence in timescales too small to comprehend. The inside of a proton is not a quiet place. It is a storm, a perpetual, contained cataclysm. This storm, this cage, is the source of the world. This is the true bedrock of your existence. Not a rock at all, but a tempest in a teapot, multiplied trillions upon trillions of times over to form the calm, placid object you call your body. Does that not feel strange? To know that your stillness is composed of unimaginable violence, that your silence is made of a constant, roaring scream trapped within the confines of a force. To understand how we came to this bizarre conclusion, we must travel back in time. We must visit an era when physics was lost in a forest of its own making. The year is 1964. The world of particle physics is in a state of chaos. For decades, scientists have been smashing atoms together with greater and greater force. And in the debris of these collisions, they found new particles. Dozens of them. First a few, then a flood. They had fanciful Greek names: pions, kaons, lambdas, sigmas, deltas, omegas. It was a zoo. A particle zoo with no apparent rhyme or reason. Nature, which had always revealed an underlying simplicity and elegance, from planets to atoms, suddenly seemed messy, arbitrary, and needlessly complex. Why so many particles? What were they all for? It was as if you took a watch apart and found not gears and springs, but hundreds of strangely shaped, unrelated pieces of junk. This was a crisis. Not a crisis of data. They had plenty of that, but a crisis of understanding. The universe, for a moment, had stopped making sense. Into this chaos stepped a man of formidable intellect, a man as comfortable with linguistics and archaeology as he was with quantum field theory. His name was Murray Gell-Mann. He was a poet-scientist, a man who saw patterns where others saw only noise. He looked at the particle zoo and, like a naturalist categorizing 1,000 species of beetle, began to group them. He found a hidden symmetry, a beautiful mathematical pattern that organized the chaotic menagerie into neat, orderly families. He called his system the Eightfold Way, a nod to the teachings of Buddhism. It was elegant. It was powerful. It predicted the existence of a new particle, the omega minus, before it was ever found. When experimenters at Brookhaven National Laboratory found it, exactly where Gell-Mann's theory said it would be, the Eightfold Way was confirmed. It was a triumph of order over chaos. But the pattern itself demanded an explanation. It was like discovering a periodic table for particles. The periodic table of elements worked because all the elements were made of the same few components: protons, neutrons, and electrons. The patterns of chemistry were the result of the patterns of their constituent parts. Gell-Mann proposed that the same must be true for his particle zoo. All these different particles, these baryons and mesons, were not fundamental. They were composite. They must be made of something smaller, something more fundamental. He needed a name for these hypothetical building blocks. The mathematics required them to come in threes inside particles like protons and neutrons. He was reading James Joyce's strange, dreamlike novel, Finnegan's Wake, and came across the line. 3 quarks from Mustermark. Quark. The word was playful, nonsensical, almost a joke. It captured the tentative, almost unbelievable nature of his own idea. At the same time, another physicist, George Zweig, working independently at CERN, had a similar idea. He called his fundamental particles aces, but Gell-Mann's whimsical name was the one that stuck. It was as if physics itself knew this new chapter required a name that defied easy definition. And here, the first great paradox arose. The model was perfect, too perfect. It explained everything. But for it to work, these quarks had to have properties that were, to put mildly, bizarre. They had to have fractional electric charges like plus 2/3 or minus 1/3. No particle ever seen had anything but a whole integer charge. It was a fundamental rule. To propose a fraction of a charge was like proposing half a person. It was heresy. Worse, no one could find one. They tried. Oh, how they tried. They smashed protons with incredible energy, hoping to chip a quark off. They sifted through moon rocks and deep ocean sediment, hoping to find a stray quark left over from the Big Bang. They looked everywhere, and they found nothing. Not a single, solitary, free quark. The particles were a ghost story. Their presence was felt everywhere, in the neat patterns of the particle zoo, in the successful predictions of new discoveries. but they themselves remained invisible. For years, many physicists, including Gelman himself at times, believed they were nothing more than a useful mathematical fiction, a clever accounting trick. How could something be the fundamental building block of everything, and yet be impossible to find? It was a question that struck at the very heart of what it means for something to be real. Is a brick real if it can never exist outside a wall? The universe was guarding a secret. Nature refused to show its hand. To solve this mystery, we must dive deeper into the strange taxonomy of the quarks themselves, into the rules that govern their unseen world. The theory proposed not just one kind of quark, but a whole family of them. They are organized into 3 generations, each a slightly heavier echo of the one before it. They are given names that sound more like flavors of ice cream or poetic concepts than fundamental constituents of matter. There is the first generation, the up quark and a down quark. These are the workhorses of the universe. An up quark has a charge of plus 2/3. A down quark has a charge of minus 1/3. Combine 2 UPS and 1 down, and you get a proton with a total charge of plus 1. Combine 1 up and 2 downs, and you get a neutron with a charge of 0. All of the stable matter in the universe, you, me, the stars, the planets, is built almost exclusively from these 2. Then comes the second generation, more exotic and unstable. The strange quark and the charm quark. They are heavier, and they only appear in the debris of high-energy collisions, living for a fleeting moment before decaying back into their more stable cousins. The strangeness was so named because the particles containing them lived for a strangely long time before decaying. Charm was named out of pure whimsy, a feeling of delight at the symmetry of the system. And finally, the third generation, the titans of the quark world. The bottom quark and the top quark. They are staggeringly heavy. The top quark, the last to be discovered, is as heavy as an entire atom of gold, yet it is a point particle with no discernible size. It is so unstable its lifetime is almost too short to measure. It exists for an instant and is gone, a brief, massive flicker in the quantum foam. 6 quarks, 6 flavors. These are not flavors you can taste. They are 6 different modes of being. 6 fundamental vibrations in the quantum field that underpins reality. But this taxonomy, this list of ingredients, is not the most important part of the story. The most important part is the rule that binds them, the force that keeps them prisoners. It is called the strong nuclear force, and it is unlike any other force you know. Gravity and electromagnetism both grow weaker with distance. The farther the Earth is from the Sun, the weaker the gravitational pull. The farther you move a magnet from a piece of iron, the weaker its attraction. This is intuitive. It is the logic of our world. The strong force laughs at this logic. It does the opposite. The force between 2 quarks behaves like an unbreakable cosmic rubber band. When the quarks are close together, inside their proton cage, the band is slack. They can jiggle around almost freely, but try to pull one of them out. Try to stretch the band. As the distance increases, the force does not weaken. It grows stronger. In fact, it remains constant, pulling back with immense power. You pull and pull, stretching this energetic band, pouring more and more energy into the system to fight the growing tension. You keep pulling, thinking that eventually, surely, the band must snap. And it does. But what happens when it snaps is the core of the entire mystery. The energy you have poured into that rubber band, the energy of the strong force field, carried by particles called gluons, becomes so immense that it reaches a critical point. And at that point, Einstein's most famous equation takes over. E equals mc squared. Energy can become mass. From the pure energy of the stretched band, a brand new pair of quarks flashes into existence. A quark and an antiquark. The new antiquark pairs up with the quark you were trying to pull out. The new quark pairs up with the one left behind in the proton. You did not succeed in isolating a quark. You only succeeded in creating more of them. You started with 1 proton, and you ended up with 2 new composite particles. You broke the cage, and in doing so, you created two new cages. This is called confinement. It is the absolute, unshakable law of the quark world. No quark can ever exist alone. Its very nature is to be bound. Its existence is conditional, relational. So, if we can never see one, how can we be so sure they are there? If every attempt to grab one fails, what makes us believe they are real at all, and not just some elaborate theoretical construct? The answer comes not from seeing them, but from seeing their shadows. In the late 1960s, at the Stanford Linear Accelerator Center, or SLAC, physicists conducted a series of landmark experiments. They built a 2-mile-long gun that fired electrons at incredible speeds. Their targets were simple protons. At the time, there were two competing ideas about the proton. If the proton was a soft, gooey blob of charge, as some models suggested, the electrons should pass through it like bullets through mist, deflecting only slightly. But if Gell-Mann was right, if the proton contained tiny, hard, point-like constituents, quarks, then some of the electrons should hit these hard points and ricochet off at sharp, dramatic angles. Imagine throwing a handful of sand at a cloud of smoke. The sand will pass right through. Now, imagine throwing the sand at a bag of marbles hidden inside the smoke. Most of the sand will still miss, but every now and then, a grain will hit a marble and fly off in a surprising direction. That is exactly what they saw. Most of the electrons pass through, but a small, significant number of them bounce back hard, as if they had struck something tiny and unyielding inside the proton. These were the shadows on the wall of Plato's cave. The physicists could not see the quarks themselves, but they could see their effect on the world. They had probed the proton and felt the hard marbles inside. This was the moment the core transitioned from a clever mathematical trick to a physical reality. They were not just a fiction. They were there. The ghosts were real. And with that confirmation, the paradox only deepened. We now had definitive proof of the existence of something that we also knew could not exist on its own. Reality was playing a new kind of game, with rules that seemed designed to confound our deepest intuitions about what it means to be a thing. Think about what this implies. Every object, can be broken down into its constituent parts. A house can be dismantled into bricks. A brick can be ground into powder. The grains of powder can be separated into molecules. The molecules can be split into atoms. The atoms can be stripped of their electrons. But the proton refuses this final step. The chain of deconstruction, the fundamental logic of made of, breaks down at the door of the proton. You cannot take a proton apart to get 3 quarks. You take a proton apart, and the energy of your action simply creates more complex particles. The universe will create new matter from pure energy rather than allow you to see a quark by itself. This is not a technological limitation. It is not that our machines are not yet strong enough. It is a fundamental law of nature. It is as if the universe has a metaphysical principle. Thou shalt not behold a naked quark. This principle of confinement amplifies the strangeness. It introduces a new logic. The existence of a quark is not an independent fact. It is a relational fact. A quark exists only in relation to its partners. Its identity is subsumed into the collective identity of the proton or neutron it helps to build. Does this challenge our notion of individuality? If the fundamental components of our own bodies lack true individuality, what does that say about our own sense of self as a distinct, separate entity? Are we, too, just a collection of relationships, a pattern whose meaning is lost if you try to examine the parts in isolation? The paradox is further intensified when we look closer at the proton's composition. We say a proton is made of 3 quarks, 2 UPS and a down. This is called its valence quark configuration. But this is another simplification, another partial truth. The reality is far more chaotic and magical. The strong force that binds the quarks is carried by particles called gluons. These gluons are not just passive messengers of force. They are intensely active. They carry a type of charge called color charge, another whimsical name for a property that has nothing to do with visual color. It is a quantum number that must always be balanced, always neutral, or white in any observable particle. A quark can be red, green, or blue. An antiquark can be anti-red, anti-green, or anti-blue. The rule of confinement is a rule of color. You can only have combinations that are color neutral. 3 quarks, 1 red, 1 green, 1 blue, make a white baryon, like a proton. A quark and an antiquark, a red and an anti-red, for example, make a white meson. A lone-colored quark is forbidden. But here is where it gets truly strange. The gluons that hold the quarks together also carry color charge themselves. They are constantly interacting, splitting into more gluons, and for brief moments, creating pairs of virtual quarks and antiquarks from a vacuum. The inside of a proton is not 3 quarks held by a few gluons. It is a seething, churning sea. It is your 3 valence quarks, the permanent residents, swimming in a roiling soup of countless virtual gluons and virtual sea quarks that pop into and out of existence, borrowing their being from the quantum foam for impossibly short moments. The proton is a crowd. It is a party where only 3 guests are on the official list, but the house is packed with countless gatecrashers who flicker in and out of the room. And this leads to the most astonishing realization of all. Where does your mass come from? You would think it comes from the mass of your constituent parts. Add up the mass of all the atoms, the protons, the neutrons, the electrons. Let's try. The mass of an up quark is tiny. The mass of a down quark is slightly larger, but still minuscule. If you add up the rest mass of the 3 valence quarks in a proton, you account for only about 1% of the proton's total mass. 1%. Where is the other 99%? Where is the bulk of you? It is not in the particles. It is in the energy. It is the furious, kinetic energy of the quarks rattling around in their cage. And even more, it is the immense potential energy stored in the strong force field, in that stretched and humming cosmic rubber band that binds them. Your mass is not substance. Your mass is the energy of confinement. È uguale a mc al quadrato. You are not made of things. You are made of the fury that holds those things together. You are a construct of pure force, given the illusion of substance. Let that sink in. The tangible, weighty reality of your body is a manifestation of binding energy. You are a slow-burning fire of contained forces, stabilized into the pattern you call a self. This is the ultimate deconstruction. We started by questioning the solidity of your hand, and we have arrived at the conclusion that even its mass is an emergent property of energy. The ghosts are not just in the machine. The ghosts are the machine. Now we must make the leap, from the subatomic to the self, from particles to the person. What does it mean for you, a thinking, feeling being, to be built from this foundation of paradox and illusion? If the components of your body cannot be said to have an independent existence, can you? You think of yourself as a singular entity, a consciousness residing in a body. An I, but what is this I? You are a collection of approximately 7 octillion atoms. 7,000 million atoms. Each one a tiny void, anchored by a nucleus that is itself a storm of confined quarks. You are a community, a symphony of relational existence, where each part only has meaning in context of the whole. You are a standing wave, a stable pattern in the quantum fields that permeate all of space-time. You are a resonance. For a few decades, the energy and matter that constitute you will hold this particular intricate form. But the particles themselves are not sacred. The atoms in your body are constantly being replaced. The carbon, the oxygen, the hydrogen, they were forged in stars billions of years ago. They have been part of countless other things, and after you're gone, they will go on to be part of countless more. You are not the particles. You are the pattern. You are the information. You are the specific arrangement of these quark-built storms. You are a thought that the universe is thinking. This forces us to ask an even deeper question, the question that philosophers have wrestled with for millennia. What does it mean to be real? Our common-sense definition of reality is based on object permanence, on isolatability. A thing is real if I can point to it, touch it, put it in a box, and know that it is a separate entity from other things. The quark laughs at this definition. A quark is not a thing in a box. A quark is a condition of the box itself. It has no meaning, no existence without its prison. So is the quark real? Or is the confinement real? Or are they two aspects of the same, inseparable reality? Perhaps real is the wrong word. Perhaps reality isn't a collection of nouns, but a grammar of verbs. A particle is not a thing, but a process, an interaction, a relationship. The universe is not a set of Lego bricks. It is a web of interconnected events. Nothing is truly fundamental on its own. The fundamental truth is the connection itself. This is not just philosophical speculation. It is the direction that physics itself is pointing. The quark is not an object. It is an excitation of the quark field. The electron is an excitation of the electron field. The photon is an excitation of the electromagnetic field. Reality, at its most basic level, is not a world of particles. It is a world of fields. Imagine an infinite, invisible ocean that permeates every inch of space. A ripple in this ocean, a localized vibration, is what we perceive as a particle. You are not a collection of tiny marbles. You are a complex, interacting set of ripples on a dozen different cosmic oceans, all overlapping and influencing one another. And this brings us to the most speculative, most profound, and perhaps most unsettling idea of all. If everything is just patterns and resonances in underlying fields, what about consciousness? What about the I that is perceiving all of this? Could it be that consciousness itself is an emergent quantum phenomenon? Not something separate from the physical world, but a property of it when matter and energy are arranged in a sufficiently complex and interconnected pattern, like the one inside your brain. Is your awareness a kind of stable resonance in the quantum fields of your neural network? Is a thought a cascade of quantum decoherence events, a wave function collapsing into a definite state? This is the frontier where physics, neuroscience, and philosophy meet and bleed into one another. We have no answers here, only beautiful, terrifying questions. The story of the quark is not a finished one. For a long time, the rules of confinement seemed absolute and simple. Quarks came in twos, mesons, or threes, baryons. That was the law. Red, green, blue makes white. Red and anti-red makes white. Simple. But the universe is more creative than our theories. In recent years, physicists have begun to find evidence for new forms of matter. Strange, exotic beasts that defy the simple rules. They have found hints of tetraquarks, 4 quarks bound together in a fleeting, exotic molecule of matter. 2 quarks and 2 antiquarks. They have found evidence for pentaquarks, 5 quarks huddled together, 4 quarks and 1 antiquark, a bizarre, complex family that does not fit neatly into the old categories. These discoveries are like finding a new continent on a world you thought was fully mapped. They tell us that the rules of the strong force, the grammar of reality, are more flexible, more nuanced than we ever imagined. The universe can write more complex sentences than we knew. There are new colors in its palette. What other combinations are possible? What other forms of matter are out there, waiting in the debris of a cosmic ray collision or in the heart of a neutron star, built from quark architectures we have not yet dreamed of? The mystery is not shrinking. It is expanding. So, let's return, after this long journey, to the original question. The question that has haunted this entire exploration. Are quarks real? Perhaps now you can see that the question itself is flawed. It carries the baggage of our macroscopic, classical intuition. It assumes real means a thing you can hold and isolate. A quark is not real in that sense, but a quark is not unreal either. It occupies a third state, a quantum state of being. It is a potential. It is a relationship. It is a mathematical necessity that has physical consequences. A quark is as real as a knot. You cannot isolate the knotness from the rope. The knot is not a separate object added to the rope. It is a configuration of the rope. You cannot put the knot in a box without the rope. Yet, the knot is undeniably real. It has properties. It has a location. It has a profound effect on the rope. Quarks are the knots in the fabric of space-time. They're the fundamental configurations of the quantum fields that give rise to the world of substance. They are the reason the rope of reality does not simply lie flat and featureless. They're not the bricks of the cosmic cathedral. They're the principle of the arch, the idea of the buttress, the law of the keystone. They're the architectural rules that allow substance to exist at all. They're the invisible grammar that allows the universe to speak. Look at your hand again. See it now not as a solid object, but as a temporary, stable pattern of unimaginable complexity. See it as a trillion tiny storms, each one a cage of energy confining the ghosts of reality. See the mass of your hand not as substance, but as the music of those cages, the humming energy of confinement. You are not made of matter. You are made of the rules that govern matter. You are a story written in the language of the strong force, a story of relationship, of confinement, of emergence. You are a brief but beautiful knot in the rope of being, a fleeting, self-aware pattern in the great cosmic tapestry, a question that the universe has learned to ask itself. And the answer, whispered back from the heart of every atom, is that the mystery is the point. The relationship is the reality. The search is the destination. You are not an observer of this strange and wonderful cosmos. You are its substance. You are its witness. You are its proof. You are woven from the ghosts, and that does not make you less real. It makes you infinitely more interesting.